All right, let me go ahead and present specifically this one screen. And this video is going to be for differential equations, section 8.3, day 4, which is the last of the textbook topics before we get to the octave programming, MATLAB programming section. So let's see, it looks like I might have a typo here, but yeah, this is the day 4 video. Day 4, higher order differential equations as systems. All right, so this is one other topic. Now, this topic is not really even mentioned in the textbook, but we're going to need it because we're going to need this in our octave unit where we learn octave MATLAB programming. And that is that if you have a higher order differential equation, a single differential equation, interestingly, you can write that as a system of first order differential equations. And that turns out to be really helpful. If you have a DE that you can't solve using existing methods, then you can rewrite that higher order differential equation as a system and then use system methods to solve. Let me show you with a simple example first, and then a much more complicated example. So just to illustrate the idea of it, if you had this differential equation here, y double prime minus y prime minus 6y equals 0, we already have methods to solve this, right? We could use the auxiliary equation, m squared minus m minus 6, factor it, get the two factors, the two roots, 3 and negative 2, and then write that as c1 e to the 3x plus c2 e to the negative 2x, right? So single differential equation, right? We have a method to solve. You can write this as a system, though. So let me show you how that works. What you do is you take the original differential equation and you solve it for the highest order derivative. So that would be y double prime is equal to, if we just move these terms to the other side, 6y plus y prime. And you write this in order from y to y prime and so on, from the lowest derivative to the highest, which the first one's a non-derivative term. And so then you enter that as the bottom row of a system of differential equations. And then above it, so if I have what y prime is equal to, the next derivative down is y single prime. And so I'm just going to write that as y prime is just equal to y prime with 0 y's in there, right? So y prime can also be written as 0y plus 1 y prime. And then what we're going to do is we're going to say, let's define our variable vector x to just be y prime. And that means we can write this in matrix form. This is just x prime. And then we have the coefficient matrix 0, 1, 6, 1 times x. So we took this one differential equation and we converted it into a system of differential equations, okay? And then we can use differential equation methods to solve. Now, if we did that, we would do something like use the determinant to find the eigenvalues, right? So this one happens to produce eigenvalues of 3 and negative 2. And then you could find the eigenvectors for each of those by plugging in the lambdas, doing the RREF, and picking a corresponding eigenvector, right? Same thing for this one. And then building the matrix solution would be C1, 1, 3 e to the 3x plus C2, 1, negative 2 e to the negative 2x, right? So the top row of this is what y is equal to. So you get the solution to your original differential equation in the top row of your system. And for free, you get what y prime is also. So you get the solution as well as the derivative of the solution. Okay, and that matches what we did with our existing method. Right, so a second way to do a single differential equation that's at least of order 2, and this works for any higher order derivative. So why would you do this, right? This is more work. In this case, our existing methods are better. But you would do this when you have a higher order differential equation where you don't have other methods that work. It also works with non-homogeneous differential equations, but then the system ends up, you still have to go through that process where you do the variation of parameters with the fundamental matrix. So you're still going to have to take an inverse matrix, but that's solvable too. I showed you an example here that was homogeneous, that has 0 on the right-hand side, but you can do this with non-homogeneous systems too, including ones that are very difficult to solve with the other methods. All right. The other reason that we're going to need this is that Octave MATLAB it has a method that allows us to solve first order differential equations And sometimes we can trick it into solving second-order differential equations with the main method. But for higher orders, we typically write it as a system. So that system of first orders, because it does have the ability to come up with a numerically based solution for systems of first order differential equations. So we take advantage of this when we use Octave or MATLAB programming later. Now, in order to do this for, say, a third derivative or higher, we're going to have to be able to take an inverse of a 3x3 matrix, which I mentioned earlier that we know how to take the inverse of a 2x2 matrix, right? It's 1 over the determinant of A times we swap the A and D and we take the B and C and make them negative. So what do we do if we have a 3x3 matrix? Well, the procedure is similar to this, but it's a little different. So let me kind of go over it real quick, because in the example we're going to do next, we're going to end up having to do an inverse of a 3x3 matrix. So let's say we had this matrix, this coefficient matrix A, which was A, B, C, D, E, F, G, H, K. I'm omitting I here and J. Okay, so then we can find something called the signed cofactor matrix. So that's like the determinants that if we were to normally pick a row to do a determinant, and then we're going to multiply this by the determinant over here, this determinant over here is called a signed cofactor. Okay, so for example, for this A here, we would be taking the determinant where we cross off this row in this column, and that would be the determinant of E, F, H, K. So I'm writing that here. And then when we multiply this B, right, it would be the negative of the determinant D, F, G, K, because you eliminate that row and column, right? And for this C here, it would be positive, the determinant D, E, G, H. Well, you could do that for all of the entries in the matrix. For example, this one in the middle, it's positive, negative, positive, negative, positive, negative, positive, negative, positive. This one would be positive, but we would be omitting this row and this column, so it would be ACGK, ACGK. So this is the signed cofactor matrix, where the pluses and minus signs are accounted for, and it's all the little determinants that you have to multiply these coefficients by. So if you were to write these determinants and compute them, and maybe I could write this as C1, 1, C2, 1, C row 3, column 1, C row 1, column 2, and so on, then what you do is you take this signed cofactor matrix of your coefficient matrix, and then you find something called the transpose. So it's kind of like the 3D version of this. What we're going to do is we're going to take all of the rows and write them as columns instead, and all of the columns get written as rows. So this row here becomes this column here, this row here becomes this column here, and this row here becomes this column here. So you just invert them that way. So what happens is the ones on the main diagonal stay the same, but the other ones get swapped. Basically, these elements get swapped as you go across. That's called a transpose. Okay, so it turns out that the inverse of a matrix is 1 over the determinant times the transpose of the signed cofactor matrix. That's true for all higher dimensions, right? And so for 3x3, we're going to use this method to do the inverse. You'll see it in action when we actually do the example next. Okay, to show you how this would work, where you write a higher, more complicated, higher order differential equation as a system, let's take this non-homogeneous single differential equation, y triple prime minus y double prime minus 4y prime plus 4y equals 5 minus e to the x plus e to the 2x. Okay, first writing it as a system, we would solve for the highest derivative, which is y triple prime, by bringing all this other stuff on the other side and writing it in order with the y term, the y prime term, the y double prime term, and then the non-homogeneous stuff. Okay, so if we wrote that as a system, then this right here would become the bottom row of the system, just as is. Right, the y double prime, one less derivative, would just be 0 y's, 0 y primes, 1 y double prime, and nothing extra. And then the next lower derivative, y prime, would be 0 y's plus 1 y prime plus 0 y double primes plus 0. And so if we now say that the matrix X is y, y prime, y double prime, then this side here is X prime plus the coefficient matrix 0, 1, 0, 0, 0, 1, negative 4, 4, 1 times the matrix X, and then plus a matrix containing all of this, 0, 0, and the right-hand side just in the bottom row, zeros above. So this is the matrix form of this equation. And we're going to want you to be able to write things and convert them from this form into the matrix form. In fact, I believe that's on the test, if I remember right. All right. So now let's go ahead and solve this solution. Let's come up with the solution of this matrix, this system of differential equations. Now, these are all first order differential equations because ultimately they only are derivatives that are one lower than where they are, right? But basically, each one of these is a single differential equation. And let's go ahead and use our methods to solve. First, we would solve the corresponding homogeneous, where we temporarily set this to 0. Right? We would use the determinant equals 0 method with these values minus lambda. So we're subtracting lambda from each of these first, finding the determinant. Now this is a little more involved with 3 by 3. We can pick one of the rows here like this one and say, okay, this times the signed cofactor here, so positive this times the determinant here, so this times this minus this times this, that's this part. And then minus 1 times 0 times this minus 1 times 4, and then plus 0 times, and then I didn't bother to write this stuff in here. And if you carefully boil that down, you'll get a third order polynomial for the eigenvalue. This one actually works in integration by group, or factoring by grouping. So if I group these and factor out a lambda squared here and a negative 4 here, I can then factor out the lambda minus 1. I get lambda squared minus 4, which then further factors as a difference of squares into lambda minus 2, lambda plus 1. So this particular determinant, this particular coefficient matrix has 3 distinct real eigenvectors, 1, 2, and negative 2. And then to proceed, we would find a corresponding eigenvector for each one. So for the lambda 1, we could go back and calculate that with 0 for right-hand side, do RREF, take the equations, and then we get that K1 is equal to K3 and K2 is equal to K3. So 1, 1, 1 is a convenient eigenvector. And for lambda is 2, if we go over here and subtract and go negative lambda, so we plug 2 in for these lambdas, and then do RREF and write the equations out, we're going to get that K1 and K2 can be rewritten in terms of K3. There's fractions here, so it's convenient if you make K3 4, because then K2 is half of that, so it's 2, and K1 is 1/4, which is 1. So 1, 2, 4 is a convenient eigenvector for lambda's 2 eigenvalue. And for the negative 2 eigenvalue, you go through the same process and you end up getting 1, negative 2, 4. So that means our complementary solution would be C1 times 1, 1, 1 e to the positive 1x plus C2 1, 2, 4 times e to the 2x plus C3 1, negative 2, 4 times e to the negative 2x. All right, so we're at that point now. We have to deal with the right-hand side. So at this point, we would use these things here along with these to write out the particular, or the fundamental matrix, right? So this is going to be e to the x, e to the x, e to the x for the first column, 1 e to the x, 2 e to the x, 4 e to the 2x. So these are all e to the 2x's. E to the 2x's, 2 e to the 2x, 4 e to the 2x here, and then 1 e to the negative 2x, negative 2 e to the negative 2x, 4 e to the negative 2x for the third column. Then we need to find the inverse matrix of this, and that requires that we're going to take the determinant first. So I could pick whichever rows I want to do. I'll pick the top row here and take this first one times the determinant of what's left when you cross those out, minus this element times the determinant of what's left when you cross out the row and column, plus e to the negative 2x times the determinant when you cross off that row and column. And then carefully finding these. 2 times 4 is 8, but e to the 2x times e to the negative 2x, these cancel on this e to the 0, which is 1. So this just ends up being 8 plus 8, which is 16. Over here, we have terms that are e to the x times e to the negative 2x. So that's going to be e to the negative x. And then same thing here. And then when we get this one, we have terms that are in the form e to the x times e to the 2x, so we have e to the 3x terms here. And then when we multiply by the cofactors here, we end up with 16 e to the x minus 6 e to the x plus 2 e to the 2x. That should be a 2x there. So, is that right? No, sorry, that's just an x. sorry, back up. That's an x, typo. So everything is all e to the x, so it ends up being a total of 12 e to the x. That's the determinant. Now we're still working on finding the inverse. We know that it's going to be 1 over this times the transpose of the cofactor matrix for this. Normally we would be at the point now where we would be reversing this, right, and putting a negative here. But for 3 by 3, we have to find the cofactor matrix for this, and we have to take the transpose. So on the next screen here, I'm going to write out for that phi matrix the cofactor matrix. So for example, in this spot, I'm going to take the determinant of these 4 right here and write that out. All right, and then I'm crossing out that particular row and column and putting the other elements that are left into a matrix. So here's that sign cofactor matrix. You can pause the video and carefully look at this to make sure this is correct and you understand how it's working. And then we'll compute each of these, which is quite a bit of work. So you take, this times this minus this times this and write the result here. Same thing down here, right? This times this minus this times this is what we write here. And so if you carefully go through all the arithmetic here and get the exponents right and all that, you'll end up with this. Okay, next what we have to do is take the transpose of that, which means we have to write these columns as rows. So in the next step, we take the transpose. Here was that. This now becomes this column. This row here becomes this column. This row here becomes this column. And finally, we take that and we multiply it by 1 over the determinant, which was 12 e to the x. So if you multiply this in everywhere, you end up getting 12 over 16, which is 4/3. And then this is e to the x, but on the bottom, so it's e to the negative x. 0. Same thing here. So all these ones become e to the negative x. When you take the e to the negative x here on the bottom, or e to the negative x, and then multiply by another e to the negative x, you get e to the negative 2x for all of these terms. And the coefficients here are negative 1/2, positive 1/4, positive 1/4. When you take the e to the 3x and divide by an e to the x, you get e to the positive 2x. So all these are e to the 2x's. And you have different constants here. So here is the inverse of the fundamental matrix, which I need in order to produce my particular solution. Okay, the formula for the particular solution only is the fundamental matrix times the integral of the the inverse of the fundamental matrix times the non-homogeneous part matrix from the initial equation. So that's going to be this matrix, the fundamental matrix, times the integral of the inverse of that matrix, which we carefully calculated by hand, times the f, which has the right-hand side in the bottom spot and 2 above it that are both zeros for the y prime and the y, or the y double prime and the y prime, since this row represents y triple prime, right? Right, carefully, we would multiply the matrices over here. So for example, let me show you kind of what's going on. If you were to, we've got a 3 by 3 matrix here and a 3 by 1 matrix here. So when we multiply, we're going to get a 3 by 1 matrix, right? 3 rows, 1 column, just 1 column, but 3 rows. So you're taking this times this plus this times this plus this times this, right? So we end up with and all of that gets written here, right? And then in the second row, we're taking this times this plus this times this plus this times this and writing the result here. You can carefully go through and see when you take all those out and combine like terms, you get this. Same thing here. If I take this times this plus this times this plus this times this and write that all out here and combine like terms, I get this. So the reason why there's not as many terms is that many of them have the same exponent, so I combine them together. So the first thing is you have to multiply this matrix. Then you have to take the integral of each of these rows. So the next thing, we're going to take the integral. We'll have still a matrix, but it'll now have the integral of this row, the integral of this row, the integral of this row. So with respect to x, if you carefully take the integrals, we get this. Now there's no more integral sign. And then we have to take that and multiply that on the left by the fundamental matrix again. So again, we've got, let's see, a 3 by 3 matrix this time times a 3 by 1 matrix. This, with these plus signs, this is all one big term. So we're going to end up getting a 3 by 1 matrix, 3 rows but 1 column. So for example, we're going to take this times this plus this times this plus this times this, and that produces this. Okay. Then we're going to go back for the second row and take this times this plus this times this plus this times this to produce this. You can carefully go through and check this in the notes to see that you can understand what's going on. This times this plus this times this plus this times this produces this. And then what I've done in the next step is just slowly gathered like terms and cancel things. So this is the particular solution. And to get the general solution, I would then add this to the complementary solution. So now that we have the particular solution, we can add that on with the particular solution, which has the constants. But then there's in some cases where there's elements that have the same form in the particular solution in here. For example, I have an e to the x term here, but there's an e to the x term here. So since I already have a constant in here, right, all of these are just going to kind of go away because those are going to get absorbed into this constant. Right, there are other constants. So basically C1 plus C2/9, whatever, these constants are all going to be, I'm just going to replace this with a new constant, C4. All right, and then I'm going to say, all right, same thing here. I've got some e to the 2x terms here. So all those constants are going to get absorbed in here. So I have a new constant here. I don't have any e to the negative 2x's, so none of that's absorbed. So all the rest of these terms stay the same. And that means this is the general solution. A lot of times this would be written this way, where we split this up. So we have a constant, which is just 4/5, 0, 0. We have an x e to the x, which has constants 1/3, 1/3, 1/3. And we have an x e to the 2x, which has constants 1/4, -1/2, 1. And then remember, the top row is the solution to the original differential equation, because this is y triple prime down here, right? Or sorry, y double prime, y prime, and y. So this top row here is the solution. So 1 times c4 e to the x plus 1 times c5 e to the 2x plus 1 times c3 e to the negative 2x plus 5/4 plus 1/3 x e to the x plus 1/4 x e to the 2x. This second row here represents what y prime is, and the third row is what y double prime is. All right, so that's a way to use this to solve a third order non-homogeneous differential equation as a system. All right, so a fair amount of work. So we're not going to really do the work itself, but because we're going to need this for the MATLAB part, we're going to have to get good at going from a single equation to a system. So let's just do these two problems here as practice. Go ahead and pause the video and see if you can just write these two equations as a system, but then don't solve the system. Just write them as a system. And I'll show you after we unpause the video how we do this, and also how we handle the initial condition, because we can do that as well. Okay, assuming that you've tried after pausing the video to write this as a system, this one should turn out. Let me use blue for this one. We would solve this for the lowest order derivative, right? I'm going to write that down here on the bottom. Y double prime equals, if I move this term over, it's -5y minus 4y prime plus 35 e to the negative 4t. And that means I have to have a y prime here. So it's going to be 0 y's plus 1 y prime plus nothing else. So if I define my x to be y prime, then that means that this over here can be written as x prime equals the coefficient matrix. First column is 0, -5, 1, -4 times x. And then I'll have a matrix here for the non-homogeneous part, 0, 35 e to the negative 4t. That's the F matrix. Okay, the last thing which I didn't really say is, what do you do as far as writing what this is? This is an initial value, right? So if x is this, then you can just say, okay, this initial value is equivalent to writing x at 0 is equal to the matrix negative 3, 1. So just tack this on as well. So the answer to this would be, here's the system, and here's the corresponding initial value written in matrix form. Okay, and then for the second one, we have a third order equation. So let me get a little more room here. I'll use a different color. Let's use purple. Okay, so first I've got my y triple prime equation. I'm just going to solve this by moving everything else to the right. So I'm going to have negative 8y. It looks like I have no y prime term, so I'm going to put a placeholder in there. And then I've got minus 2y double prime, right? And then I've also got this plus 8t squared plus 2t minus 5. So the next lower derivative would be y double prime. So that's no y's, no y primes, one y double prime, and nothing else. And then since this is a third order, I'm going to have a third equation here for y prime. 0 y's, 1 y prime, no double primes, nothing else. So if I define X to be the matrix y, y prime, y double prime, then that means that this is X prime equals 0, 0, negative 8, 1, 0, 0, 0, 1, negative 2 times X plus a matrix with 8t squared plus 2t minus 5 on the bottom and 0 above it. So this right here would be the matrix if you define this as X. And then to handle this initial condition, we can just write that as X0 is equal to the y value, the derivative value, and the second derivative value. So this would be the corresponding initial condition written as a matrix. And that's all we'd be looking for on the test, something like that. All right, that should be enough to give some of the homework a try.